In this question, we're given the model of an atom, and the energy is in zeptojoules, which is 10 to the minus 21 joules. And we're asked some questions about electrons on this model. So what's important to note is this is actually where light is coming from. So if we have an electron in the ground state and we thermally or electrically excite it to a higher energy level, and then it falls back down, when it falls back down due to the law of conservation of energy, that energy must go somewhere. And that energy is emitted as a photon. And that photon may be a visible light, and we can see it. So here we're looking at some different questions. So it says, what is the energy of the electron in the ground state? Well, the ground state is the lowest energy state. So the lowest energy state here is A. And if you look here, it looks like it's about 250 zeptojoules. So 250 zeptojoules is about the ground state energy. What is the energy of the electron in the first excited state? Well, if A is the ground state, B is the first excited state, and in the first excited state, it looks like it's about 600 zeptojoules. Next it says, if an electron makes a transition shown in the red arrow, this arrow is red on your screen, but I don't have a color printer, from C to B, will a photon be absorbed or emitted? Well, if an electron goes from energy level C to B, it loses energy. And due to the law of conservation of energy again, that energy must go somewhere. So where that energy goes is, it's emitted as a photon. So if an electron goes from a lower energy level to a higher energy level, a photon is absorbed. However, if it goes from a higher energy level to a lower energy level, a photon is emitted. Now it asks us to actually calculate the wavelength of the photon that would be emitted. So we can do that because it goes from 1000 zeptojoules to 600 zeptojoules. That means that this photon must have an energy of 400 zeptojoules, the difference between 1000 and 600. So these 400 zeptojoules of energy must go off as a photon. Well, using the equation E equals hc over lambda, we can actually calculate the wavelength of this photon. Because if we rearrange this equation, as I've done in other videos that are on this playlist, lambda equals hc over E, the energy. But we can't plug in the energy in zeptojoules. We have to plug in the energy in joules. So we need to convert this to joules. Well, there are one joule is, one zeptojoule is 1 times 10 to the minus 21 joules. So multiply by the top, divide by the bottom, and we find that there are 4 times 10 to the minus 19 joules. The sig figs are a little bit arguable here, but I would say that these are 0 decimal places, so I would say this 400 is more like that, so it's 3 sig figs. Now we have our equation, lambda equals hc over E, and we have our E and our energy in joules. So now we can plug in, because this is a constant and this is a constant. So lambda equals h, which is Planck's constant, 6.626 times 10 to the minus 34 joule seconds, times c, 3 times 10 to the 8 meters, that's 8 meters per second, divided by the energy that we just found, 4.00 times 10 to the minus 19 joules. In this case, lambda equals 4.97 to 3 significant figures times 10 to the minus 7 meters. So remember that this equation gives you the wavelength in meters. There are 1 billion nanometers in 1 meter, and for light that's near visible light, or in this case is visible light, it's convenient to give the answer in nanometers. So you multiply this by a billion, multiply by 1 times 10 to the 9, and you find that this is 497 nanometers, which is a more convenient unit. This is green light. So if a photon in an atom goes from C to B in this case, it will give off a photon of green light, and we would actually be able to see that green light because our eyes can see visible light.